Hello everyone. So recently I came across a very interesting blog from Netflix where they migrated from Java traditional threads to Java virtual threads and how it caused an outage at Netflix, which got me interested to learn more about virtual threads. So in this blog we'll learn how virtual threads work and we'll also see how virtual threads caused an outage, etc. So before jumping right into virtual threads, let's first understand what was the problem faced by Netflix. So, after investigating, they found that the affected instances had an increasing number of sockets in the closed wait state. Closed wait state means that the socket were closed on the remote, but they are still open on the affected instances. So, as we can see in the diagram, the number of sockets in the closed instance is very high, around 21k or 22k roughly, right? So to debug this issue, we need to understand what was happening with the impacted instances, right? Hence, Netflix team decided to take the thread dumps of the impacted systems and to analyze those thread dumps. On analyzing the thread dumps, they found that there were too many virtual threads waiting in the there were too many virtual threads without any particular stack trace, right? And the number of virtual threads was exactly equal to the number of sockets in the closed wait state. This tells us that there is this particular outage is somehow related to the virtual threads. But hold on a second, what exactly are virtual threads? So let's understand that in the next part. So what are virtual threads? Let's take a scenario first, right? Assume that you are an owner of the restaurant and you hired one head chef and there are maybe 8 to 10 line cooks, right? The line cooks would perform different tasks like baking, marinating, frying, etc., right? The different set of cooking tasks. So now let's take a scenario, let's assume a scenario in the kitchen that whatever task is assigned to a line cook requires availability of the head chef to complete that task, right? Maybe let's say there are 8 to 10 line cooks, right? So each of the line cook would wait to complete that task until head chef is at their table, or maybe they have some availability of the head chef, right? So this way you can imagine how slow would be the overall process. This is also bad for customer because this way customer will have to wait more time for his dish to get prepared, which is obviously a bad user experience, right? I mean, think of it that you ordered maybe fries, right, and you have to wait like 1 hour just so that your fries are ready. So, and other than that, this is also a burden on the head chef, right? So, as the owner of the restaurant, what would you do to solve this particular problem statement? Maybe take some time to think about it, and post that we'll go back to the how we would solve this particular, how we would optimize this particular restaurant problem statement, right? So okay, so coming back to the solution of our restaurant problem. So ideally we would plan in such a way that each line cook would work independently on the task and would only ask for availability of head chef whenever it is required, right? So as we can see in the image, there are different line cooks that they're working on that task, right? And they are waiting for head chef only when they actually need assistance of the head chef, right? This way it is much more optimized, right? So now coming back to our Java world. So in Java concurrency as well, we are facing similar issue faced by the restaurant, right? So if we try to map the Java world characters with the restaurant problem, we can think as the head chef will be the our OS level platform thread, right? Which are scarce in resource. Like in our case, we had only one head chef, and in basically machines, it would be the number of CPU that we have, right? And so the line cook so each task assigned to a thread can be mapped to a task assigned to a particular line cook, right? So you can think in this way, right? So if whenever a task is assigned to a thread, that thread will be continuously active until that task is completed, So this is similar to the restaurant problem, right, where for each task a head chef was required continuously, and without it, any task won't be completed, right? So now, since OS level thread or head chef are very limited for the system, they are a scarce resource, right? And hence this creates an inefficiency into our Java ecosystem as well. So how does a virtual thread come into picture and solve this problem? So since virtual thread, you can imagine similar to our solution to the restaurant problem, right, where virtual thread would independently work on their task and will only ask for OS platform thread whenever it is required, right? uh, okay, so let's maybe more deep dive into this, right? So before actually deep diving and understanding how virtual thread works, we need to understand what all types of tasks are there, right? So in general, we can categorize each task that we assign to a thread into two different categories. This category would be a CPU intensive operation, that is, we want to run some logic, or we want to perform some computation over the data. And another can be IO blocking operations. This basically means fetching data from somewhere. Maybe it can be a database or backend server from disk, basically fetching some data over the network, right? So OS threads are mostly useful when there is a CPU intensive operation, and in the IO operation, they would just be sitting idle and waiting for the response to come, right? So for this reason, OS thread don't actually perform well for IO operations. So for such cases, we can use help of the virtual thread. So how virtual thread works is, virtual thread would ask the OS thread to the OS thread for a CPU intensive operation, right? And whenever there is an IO operation, they would just wait independently, right, and release the OS thread, right? So hence, so that the OS thread can work on some other operation, and the virtual thread can independently wait till they have response from the IO blocking operation, right? So for entire of this video, we'll call OS thread as the platform or carrier thread, right? And hence we'll be going forward, we'll be using this same term. So now let's understand this workflow of the virtual thread with an example. Let's assume that we want to fetch some data from the database, run some business logic on it, and then publish an event regarding the outcome of the processing. So our program first would initiate a virtual thread to perform this task, right? And whenever a virtual thread is initiated, JVM scheduler would try to find a carrier thread, right, and schedule this virtual thread on that carrier thread, right? So first operation is we need to make a call to the database, right? As soon as the call is made, an IO blocking operation is started, because we will wait till we get response from the database. So once the IO blocking operation is started, our carrier thread would release the virtual thread and would go on performing some other task, right? Virtual thread would independently wait till we get response from the database, right? So once the response is received, our JVM scheduler will again try to find a platform thread on which next task can be performed, right? So let's say this virtual thread was again scheduled on a carrier thread, right? Now the next operation we have is a CPU intensive operation. That is, we want to run some logic over the data that we got from the database, right? So our virtual thread, with the help of carrier thread, will perform this operation, will perform the CPU intensive operation, and once this operation is finished, next task is to publish an event to any message broker, let's say Kafka, right? So making a call to publish an event is also a kind of CPU intensive operation. As soon as the call is made, next task is the IO blocking operation, that is waiting for the response from message broker that event has been published on the message broker successfully, right? So for this particular IO blocking operation, again our virtual thread would be suspended from the carrier thread, so that carrier thread can start performing any other task. And as soon as we get response from the message broker that yes, message broker has acknowledged the publishing of the message, virtual thread will be again scheduled on the carrier thread, and after this, our complete task would be completed and virtual thread would be also completed, right? Okay, so based on what we've learned so far, it is important to remember that virtual threads won't make your processing any fast, right? They basically give you a capability to handle more scale and more concurrency, right? So it would make more sense to use virtual threads where there is very high concurrency and most of the time your threads are spending time in some IO operation, right? So in those cases, if you use virtual threads for IO operations, your virtual thread can wait, but on the other hand, traditional threads can perform some other operation and maybe handle some more requests, right? A typical example for this where virtual threads would be more useful can be a web server, right? Where the server gets too many requests, and let's say if there's a traditional thread would wait until your entire process is complete. By process I mean, let's say your application is fetching some data from database and returning it, so a traditional thread will be alive until whole this process completes, and for this time new request will have to wait, right? So if we use virtual threads in this case, what will happen? Virtual thread will accept the request, and whenever an IO operation is made, they can wait in the memory, and the traditional threads can work on some new requests. So this way virtual threads would be more helpful here because there is very high IO operations. Okay, so let's understand what is the basically difference between virtual threads versus a normal traditional threads, right? So it is important to understand that in a normal system, traditional threads were a scarce resource, right? Because you have limited number of CPUs, so therefore you have limited number of traditional threads, and hence it was a necessity to manage them, which was done using thread pools. But since in this case, virtual threads are not a scarce resource, right? You can literally make a millions of virtual threads without leading to any major impact, right? So it doesn't make sense to use thread pool over virtual threads. So if you use if you use thread pools for virtual threads, you are not basically getting any benefit of the virtual threads. But now let's say there comes a case where you still want to control the concurrency using virtual threads. A typical example could be like your application is calling a database, but database supports only some limited number of concurrency. It can support some limited number of concurrent requests at a time, right? So in those cases, if you're using virtual threads and you want to limit the concurrency, you can use semaphores to control it, right? Now let's understand the things that you should keep in mind while using virtual thread, right? While using virtual thread, if you're using a virtual thread cannot be unmounted from the carrier or the traditional thread if it is running the code inside the blocking code, right? That is if it's running inside the synchronized block. In that case, virtual threads won't be able to unmount from traditional threads even if they are performing the IO operation, right? So with this point in mind, let's go back to our analysis at the Netflix outage to understand exactly what happened. So now that we've understood how basically a virtual thread works and in which all cases we should use a virtual thread, we can go back to our analysis that caused an outage at the Netflix, right? So let's take a small recap on the analysis. So as we saw, they found that there were too many virtual threads without any stack trace, right? This indicates that virtual threads were triggered, but they were not started. And also, as we saw in the previous image, in the previous graph, that number of virtual threads were almost equal to the number of sockets in the closed wait state, right? So further examination found that there were around there were exactly 4 virtual threads which were not able to unmount from the carrier thread, right? Like there are like 22,000 virtual threads, right? But out of them, there were 4 special virtual thread which were not able to unmount from the carrier thread or release from the carrier thread. So why exactly 4 virtual threads? One can ask. Because this instance was running on a machine which was having 4 virtual CPUs, right? And hence this machine would have basically 4 platform level thread. So this indicates that all of the platform or carrier threads of this instance were occupied by these 4 virtual threads, and hence these virtual threads were stuck for some reason, right? So as we can see in this image as well, that there are 4 virtual threads, vt1, vt2, vt3 and vt4. These are mounted on the platform or carrier threads, and they're not able to unmount, right? Hence even though new virtual threads were getting created, but JVM was not able to find any carrier thread for this threads to run, right? So this was the reason that there were too many virtual threads getting timeouts and and the instance got stuck in some in between state, right? So now we need to understand why these 4 virtual threads are stuck. So once the developers checked the code, checked basically the thread dumps at which particular line they are stuck, they found that all of these 4 special virtual threads were trying to acquire a lock inside a synchronized block, inside a Java synchronized block, right? And they all were trying to acquire a lock, but they were not able to acquire it, and hence they just got stuck on the carrier thread, right? So the question is, so since everyone was trying to acquire the lock, all of these 4 threads were trying to acquire the lock, but no one was able to. So the obvious question becomes, who has this particular lock, right? On analyzing the thread dump further, they found 2 more interesting threads. One was a virtual thread which was also attempting to acquire the lock on the same resource, but not via synchronized block, right? So as we saw earlier, since this particular thread was not trying to acquire lock via synchronized block, and it was not able to acquire the lock, our basically JVM released this particular virtual thread, and so basically JVM unmounted this particular virtual thread, and it was waiting next to acquire the lock, right? This was one virtual thread. Now there was another normal OS thread which had the lock, right? Which had the lock earlier, not currently, right? But now this particular thread has released the lock due to, let's say, timeout, right? And this thread is again going back in waiting in the queue to acquire the lock. So as we can see in the image, this is the queue for this particular lock, right? Where virtual thread 5 is at the top, right? And after that there's virtual thread 1. So virtual thread 5 is the thread that was trying to acquire lock without a synchronized block, but since it was not able to, it was unmounted. After that there are virtual thread 1, vt2, vt3 and vt4, right? And after that there's a normal thread, right? So again the question comes, so as of now, who has the lock? The answer is no one, right? To understand this behavior, we need to understand the internals of the release, right? So whenever a thread calls the release function for a lock, it releases the lock and calls the next thread waiting in the queue to acquire the lock, correct? So in our scenario, since the next in the line is a waiting, next in the queue is a virtual thread vt5, right? That wants this particular lock, and our JVM will try to find a carrier thread for this particular vt5 so that vt5 can acquire the lock. But since all of the all of the carrier threads are busy, and none of them are none of them are able to run the block of the vt5, our system is kind of in a stuck state, right? So maybe to summarize, in the queue we have vt5, which is a virtual thread that is trying to acquire lock via non-synchronized block. Then we have vt1, vt2, vt3 and vt4, right? So when the thread that was having the lock released the lock, right, it called vt5 to acquire the lock, but vt5 would require a particular platform thread to acquire the lock, and since none of the platform threads were available, our system got into stuck state, right? This is kind of a deadlock problem, and hence whole system got stuck, and there was very high number of sockets in the waiting state. The point to note here is that this issue happened only because of having a code that was running on virtual thread with the synchronized block, right? So instead of this, if they had used a reentrant lock, this particular problem would have never occurred. So let's try to summarize what we've covered so far, right? So virtual threads are a very promising new feature that Java has released, right? And they can help you in supporting very high performance in very high throughput scenarios, right? Point number one. Second point being, they should be used in a system where there is very high concurrency, and most of the time your threads are spending in the IO operation. Third point, virtual threads are not a scarce resource, so they should never be pooled while using them. Like there can be literally millions of virtual threads in a single process, and your system would still work properly, assuming that your system has enough memory. And the last point is, you should never use any monitor code with your virtual threads. That is, there should not be any synchronized block in the execution code of your execution code that virtual thread is going to perform. Right? If there is any synchronized block that is running via virtual threads, then that can lead to unexpected state like faced by Netflix, and the debugging can also be a little bit tricky. So if you have any doubts related to this topic or what we have covered so far, please drop them in the comments. I'll try to look into it and resolve it as best of my knowledge. If you want to learn more about virtual threads, how Netflix debug, what all steps Netflix use to debug this particular issue, you can check the links that I provided in the description. To learn more about this particular outage, again I've provided the links in the description. Please do check them. It is a very interesting read. Other than that, whole credit for this particular article goes to the Netflix engineering team. And the last point, if you want to cover any other future topic, if you want me to cover any other future topic, please drop them in the comments. I'll definitely take a look into it.